In the last video in our series on limits, we learned that the left limit and the right limit must agree in order to have a double-sided limit. But really, this whole premise brings up a whole different question. Why would the left and right-handed limits not agree to begin with? Well, truth be told, the answer boils down to one single thing, and that thing is continuity. Why is continuity important? Of course, as we saw last time with double-sided limits, yes, in fact, continuity is very important for limits, but it's also very important for things like derivation, which we will learn about in the not-too-soon future, and it's also important for integration. But in order to see what I mean, we have to know what continuity even is, what makes a function continuous or not continuous. So really, there's only one criteria which makes a function continuous or not, and that literally is just whether or not it has a gap. And it doesn't matter how big that gap is. For example, this arbitrary red function f of x is not continuous, obviously, because there's a giant gap in this interval. But I could also say the same thing about this arbitrary green function. Even though it doesn't have a huge old gap, it has a single point that is missing. And so this entire green function is not continuous either. The only way that a function can be continuous is if it has all points in the interval or in the entire domain as valid points. And so there's three different types of continuities that we must address in order to get the full scope of what's going on. So first, we're going to take a look at the jump discontinuity with this piecewise function f of x. But besides the fact that it cuts off down there and right there, the point I want to emphasize is the fact that there's a giant gap at x equals negative 2 pi and x equals positive 2 pi. And this gap is exactly what makes it a jump discontinuity. Now, the nice thing about the jump discontinuity is that it mostly happens just with piecewise functions. Now, of course, there are floor functions and ceiling functions, and a couple other lesser known functions, but really the only time you're really going to see this is if you're looking at a bunch of obscure data, such as in a piecewise function where it's broken up into parts, and those parts might not always align. Now, this is an important thing to note. Just because it's a piecewise function does not mean there is a jump discontinuity. So although on this piecewise function there is a jump discontinuity, if we were to have something like this piecewise function, so this is clearly a piecewise function, but it does not have a jump discontinuity. But again, I just wanted to point out the fact that piecewise functions are generally associated to jump discontinuities. Not all the time, but fairly often. The second kind of discontinuity I want to talk about is the removable discontinuity. Obviously, there's a much smaller gap, it's only a single point that's missing. But what makes it a little bit harder is the fact that we have to do something about this. In order to find which point is missing, we have to do a little bit of algebra. So what we have here is a rational function, meaning that it's basically a function divided by a function. Now we have two options here. One, we could do long division and divide it that way, but the other option that I'm going to do is factoring this top function. We need to factor that, because what factoring does is it allows us to see all the roots of this cubic function. So I'm going to go ahead and rewrite our function, but I'm going to use the factors of this cubic instead of the cubic itself. So here we are with our cubic factored out, and instead of a giant cubic like we have here, we just have x squared plus 2 times x plus 1. Now, what makes this so useful? Why does this contribute to a removable point? Well, the key lies in the fact is that we're multiplying by one of the things we're dividing by. So normally, if it was just x plus 1 by itself on the bottom, the denominator could not equal 0, because that would give us an asymptote. But again, that's only if it was just x plus 1 by itself. But it makes it a little bit better for us, because we don't just have x plus 1 on the bottom, we also have x plus 1 on the top. So what value of x would make our denominator equal 0? Well, x equals -1 would be -1 plus 1, and that equals 0. But since we also have that on the top, that means that this would also become 0. And so really the only time we would have 0 over 0 is when x equals -1. Because remember, when we're multiplying, only one factor needs to be 0 in order for it to become 0. Now here's where it gets interesting, because that's what happens if it equals 0. But for any value that is not 0, the x plus 1s on the top and bottom cancel out. And so when they cancel out, the function that we have left really is just this function right here, x squared plus 2. And again, since the 0 over 0 happened with -1, this is for any value where x is not -1. And now, doesn't that explain this whole very perfectly? This is because at x equals -1, that is the only place where our value is 0 over 0. Otherwise, these x plus 1 terms cancel out. And so, we would basically just have a functioning parabola. And so now, if we go back to our original function, the only thing we would have to clarify is that x also equals -1. And by doing so, we would be able to fill that hole right back up where it needs to be. And the last kind of discontinuity I'd like to look at is the infinite discontinuity. The function that we have here is 1 over x squared, and the reason why I'm saying that it's harder than a removable point is because these are not repairable, meaning I can't just reinsert one value of x in order to make this asymptote get away. Now I know we've talked a little bit about asymptotes in the past, and how that usually means that a limit does not exist. However, I would like to point out that just because an asymptote exists, that does not mean the limit does not exist. The mere presence of an asymptote does not mean our limit doesn't exist. As you can see here, there is a clear asymptote at x equals 0, but both sides of our function go upwards, meaning that they approach the same thing. But say I had a different function, such as x over natural log of x. In this case, the asymptote at x equals +1 does yield a limit that doesn't exist, because the asymptote goes in the opposite directions. And so what makes the infinite discontinuity the hardest is that this deals more into end behavior. We're going to deal with that in a future episode, so stay tuned for that. But remember, not only can an infinite discontinuity not be repaired, it also does not always mean that a limit doesn't exist. And so, what are the key takeaways on today's concept of continuity? Well, I think a big part of it is that continuity is very self-explanatory. All the function needs in order to be continuous is it cannot have any gaps in its domain or its range. And so hopefully all three of the discontinuities that we looked at today are a little bit more clear, and now you could use that in your arsenal when trying to work with limits. Remember to keep working hard, you're doing good, and I'll see you in the next one.